So the next session will be Spotlight Talks, and Lin Sun from Samsung will be moderating this session. I'll hand it to you, Lin.
I'm Lin Sun from Samsung Strategy and the Innovation Center. I will host our first Spotlight session. In this session, we have 4 papers from different organizations. Each paper have 5 minutes to do the presentation, and after all the presentations, we will do the 10 minutes Q&A session at the last. Do not forget to type the questions in the Q&A bottom at the bottom of the Zoom. The first paper is the latent space roadmap for visual action planning. It comes from the University of Salerno, KTH, University of Casino and South Lazio. And the presenter is Martina Lippi. Enjoy.
Hi, I'm Martina Lippi, and I'm going to introduce you our work about latent space roadmap for visual action planning. In particular, the problem that we consider is to generate visual action plans for tasks with high-dimensional state spaces, like, for example, the manipulation of deformable objects. So as we see from the picture, we are interested in both getting the visual plan, that's the sequence of images from start to goal, and the action plan, that's the sequence of actions to achieve consecutive transitions. And here, for example, an action is defined as the couple of where to pick and where to release the t-shirt. So the problem is that the traditional planning approaches can be intractable with this kind of high-dimensional state spaces. So we decided to resort to data-driven low-dimensional latent spaces that allow to achieve compact representations. But then the problem becomes how to capture in an efficient manner the global structure of the system in the latent space as well as the dynamics of the system. So to solve this problem, we propose the following approach, where the main component is the visual foresight module that gets the start and goal configurations and produces the visual plan, that is the sequence of images from the start to the goal. And in addition, it also produces a latent plan that's the sequence of points in the latent space that lead from the start to the goal configurations. And given this latent plan, we have a further module that we call Action Proposal Network that generates the action plan. So by combining visual and action plans, we get the visual action plan. And in this presentation, we will just focus on the visual foresight module that represents our main contribution. So our approach relies on a dataset composed of the following tuples, where the first element of the tuple is the image of the start state, then we have the image of the successor state, and then we have the information of whether there is an action or no action between these states. So for example, here we have a first example of action pair where there is an action between these 2 states, and then we have a no action pair where there is no action between these 2 states. So on the basis of this dataset, we can build our visual foresight module that produces the visual plans. And for this purpose, we first train a variational autoencoder with an augmented loss function that is based on the action-no action pairs. And then we build a graph-based structure in the latent space that we call latent space roadmap. And in particular, the latter allows to capture the global structure and the dynamics of the system. So the basic idea is that each node of this graph is associated with a region of valid states of the system, while each edge is associated with a possible transition between states. So on the basis of this graph, we're able to plan in the latent space from the start to the goal, and then by decoding this latent plan, we can obtain the visual plan. We validated the approach on a real-world experimental setup that's composed of a Baxter robot performing a folding task. So first of all, we define the start and goal configurations. Then we get the visual action plans to achieve the goal configuration, and we select the one to perform. At this point, we can actually execute the first action of the plan. And then we consider that we have a replanning step that takes into account possible uncertainties in executing the action. So now the start state is the current state of the system, and we get again the visual action plans to achieve the goal configuration. We select the one to perform that's now unique, and we execute the respective action. So at this point, we are ready to execute the last replanning step. So we get the last visual action plan, and we select the one to execute, and we finally execute the last action that leads to the final configuration. So in conclusion, we propose the latent space roadmap to perform visual action planning, and we validated the approach on a real-world t-shirt folding task. Thank you for the attention.
What? Oh, sorry. Sorry, the second paper comes from Deep Lab and the Technical University of Darmstadt, National Technical University of Athens, and MPII. The presenter is Georgia.
My name is Georgia Kalvadzaki, and I will present to you our work on revisiting grasp map representation with a focus on orientation in grasp synthesis. Grasping is still challenging for robots due to the high variability in the object's morphology. The continuous and effective estimation of the approach vector is fundamental for the successful grasp execution. State-of-the-art pixel-wise approaches fail to model ambiguities due to multiple overlapping grasping boxes with different orientations, and hence cannot provide sufficient reconstructions of the grasp maps. Our problems lies in finding the optimal grasp configuration, which is the grasp center, the orientation, and the jaws opening, and also a quality measure that characterizes the success of the respective grasp configuration. The Jakarta dataset is one of the biggest grasping datasets with 54,000 images and 1.1 million annotations, which are rectangles with given center, angle, width, and height. These annotations are simulated and resulting into multiple overlapping boxes considering all possible grasp orientations and different jaw sizes, where the jaw size is a free variable that can be arbitrarily chosen during the evaluation. Morrison et al. Created ground truth maps by creating pixel-wise quality, angle, and width maps by iterating over the annotated boxes and stacking binary maps. This stacking is indifferent of the order of the boxes and finally consider only maximum jaw sizes. For the angle and width maps, the annotations are overwritten by the box that appears later in the annotations. And finally, they use binary quality maps that do not ensure a valid maximum, as all points inside the box can be considered as a possible grasping center. This means that even a hypothetical regressor cannot perfectly predict and reconstruct the annotated grasping maps, as you can see from the figure. We, on the other hand, are proposing a new representation, and we partition the angle values into n bins. We do not discretize the angle values, but we instead place them inside the corresponding bins. We use soft quality maps that contain ones of the exact positions of the centers of the boxes, while their values degrade at the edges of the boxes. And for multiple instances of the same grasp center, we pick on the mean jaw size. And for evaluation, we adopt the same policy with Morrison et al. To be directly comparable. This leads us to an augmented grasp map representation that contains the new angle, width, and soft quality maps, a new binary orientation map, and a pixel-wise graspness map that contains one on the positions of the maps. For the grasp synthesis problem, we propose Orange, an orientation-attentive grasp synthesis framework that is model agnostic and can be combined with any CNN-based model that is able to provide the segmentation. In this work, we combine Orange with GGCNN from Morrison et al. And UNet that are both able of performing segmentation, and we will prove that both of these networks perform better under the Orange framework. The orange takes the augmented graph map representation and fuses continuous and discrete information, uses the pixel-wise graphness as a regularization and the beam-wise orientation attention in order to force the focus of the network on the local maxima of graphness. From our ablation study, you can see that the full proposed model with pixel-wise graphness and beam-wise orientation and tension achieves the best results in the IOU threshold of 0.25 and 0.30. While we can see that using binary maps over the soft quality maps produces 4% less accurate grasp predictions, while training the unit under the in the way suggested by Morrison et al. Succeeds only 89.85%. Compared to the other works on the Jacquard dataset, we can see that we gain the state-of-the-art performance under the orange implementation. And we can say that the innate morphological characteristics of objects may hinder the learning of robotic grasping, and structures like cyclical objects offer a wide range of plausible grasping orientations. We optimally would like to acquire a mapping of graspness of all possible configurations and then sample from the most likely configuration for achieving different manipulation tasks. And we revisited the grasp map representation by classifying the grasp into discrete orientation beams and regressed their values for a continuous estimation per beam. This orientation map acts as a beam-wise attention mechanism over a soft quality map, and we proposed orange that can be combined with any approach capable of performing segmentation, boosting its performance and generating accurate grasp predictions. Thank you. My name is Georgia.
Okay, the third paper comes from Google DeepMind. The presenter is Tim Pertwee.
Hello, my name is Tim, and this spotlight talk is about our paper, Simple Sensor Intentions for Exploration. This work was done in the context of scheduled auxiliary control, which is a multitask learning approach in which auxiliary tasks are learned alongside a main goal task, and these auxiliary tasks facilitate exploration towards the main goal task. Scheduled auxiliary control has two main ingredients. The first is shared data, which means that the transition distribution for which the policies and the queue functions are learned is obtained from a replay buffer that is filled by executing the policy for the goal task, as well as all other auxiliary policies. The second ingredient is the sequencing of intentions, which means that episodes are subdivided into multiple sequences and the policy to execute is chosen for each sequence. Like that, scheduled auxiliary control can achieve high data efficiency, which makes it fit for learning complex tasks completely from scratch on real robot systems, as long as the auxiliary tasks help with exploration. An important insight of scheduled auxiliary control, however, is that the exact definition of the auxiliary tasks isn't all that important as long as they jointly lead to adequate exploration. Previously, however, auxiliaries were usually chosen specific to the goal task, often with a lot of hand engineering and with domain knowledge encoded in the reward definition. When aiming for generality, a challenge here is to find auxiliary tasks that do not require a lot of domain or task-dependent prior knowledge, but that still provide for sufficient exploration to also learn complex tasks in a variety of domains. With simple sensor intentions, we wanted to take a step in this direction. The basic idea is that in the absence of an external reward signal, a sensible exploration strategy can be formed by learning auxiliary policies that deliberately cause an effect on the observed sensor values. What we aim for example, is to learn a policy that takes actions in order to deliberately increase or decrease the reading of a touch sensor. That obviously has a manifestation in the real world. A robot might learn to grasp an object. But the reward formulation itself is still general in the sense that it doesn't require a semantic understanding of the concrete environment. The idea targets scalar sensors, obviously, but not all robot sensors are scalar. In particular, camera images do not readily fit in this scheme. We can use a very simple approach, however, for transferring images into a representation that can then be used instead. We threshold the images with a bracket of the U-ring to derive a mask, and from this mask, we compute the distribution of active pixels along both of the image axes. We can then treat the means of these distributions as a scalar representation of that U-range on which SSIs can be applied. That loosely translates to rewarding an agent for increasing or decreasing the mean position of that specific color range along one of the image axes. We use this auxiliary setup for learning to grasp and lift the color block. Early in training, the SSIs will encourage the agent to push the block in a basket, and later the agent will learn to grasp the block and eventually also learns to lift the object. The very same auxiliary setup can be used with a much more complex goal task, stacking 2 blocks, which is a very hard exploration problem. Using only SSIs as auxiliaries, the task can be learned successfully as well. When dealing with images, we're not limited to a single color range. If we do the pre-processing outlined earlier for U brackets covering the whole U range, we can treat the means of these distributions as a representation of the whole image, on which SSIs can then be applied to. Now, depending on the use case, however, another formulation can also be interesting, in particular if we want to keep the number of auxiliary tasks low. We can total the rewards for changing individual color channels to form an aggregate SSI, and this loosely translates to rewarding the agent for changing or moving whatever color thing can be changed or moved in the environment. This approach was used in an experiment on a real robot, again, learning from scratch purely from pixels and proprioception. The goal task is to lift the object placed in the basket, and since we used the aggregate SSI formulation here, we were able to swap out the object during training, with the agent eventually learning a policy to approach, grasp, and lift arbitrary objects placed in the basket. To show the generality of SSIs, we employed the same set of auxiliaries we used before when learning to lift the green block, and we applied them to the ball in a cup task, with the SSIs now targeting the yellowish color of the ball. Early in training, the agent learns to swing the ball, which facilitates exploration for eventually learning to catch the ball with the cup. This as well is trained completely from scratch, purely from pixels and proprioception. In summary, with simple sensor intentions, we propose a reward scheme for defining auxiliary tasks that reduces the amount of prior knowledge required and that is generic and can be applied to a broad range of domains. SSIs can be computed from raw sensor streams, require none or only little task-specific engineering, and thus transfer easily to new domains and tasks. Further, we could show empirically that SSIs work well in different domains, and that SSIs provide for sufficient exploration to also learn difficult tasks.
Okay, the last paper comes from Stanford University. The presenter is Suraj Nair.
We present goal-aware prediction, learning to model what matters. Deep model-based reinforcement learning has shown promise in a number of settings, ranging from challenging robotic control to learning directly from pixels. These methods exhibit numerous favorable properties, including sample efficiency, stability, and interpretability. However, scaling these methods to diverse visual scenes poses numerous challenges, the primary of which is underfitting, even with very large models. In these settings, the learned model cannot perfectly model the scene. As a result, learning algorithms must balance how best to learn their model to achieve good performance on downstream tasks. Specifically, in many cases, there exists an objective mismatch, where better performance fitting the model does not directly translate to better performance using the model with planning the downstream tasks. We begin by investigating the relationship between model error and task performance. In this setting, we will consider the following assumptions. Specifically, that we're using a simple planner which evaluates action sequences over a learned model and selects the lowest cost action. Each action sequence will have a true cost in the environment as well as an estimated cost on the model, which will be affected by model error. Without loss of generality, let the trajectories be ranked as shown. That is, under the true clause, the planner will select action sequence 1 as the best action. We aim to understand under what conditions does the planner's behavior remain epsilon optimal. That is, the chosen action sequence has true cost within epsilon of the best true cost when planning under the learned model and estimated cost. We showed that if the prediction error on the best trajectory is bounded by epsilon, and the prediction error on the suboptimal trajectories are bounded by their distance to the optimal trajectory, then the planner will remain epsilon optimal. Note that the allowable error bound scales with how far from optimal the action sequence is. The key takeaway being that to maintain task performance, the greater the true cost of the trajectory, the more prediction error we can afford. Motivated by this analysis, we asked the question, how might we encourage a learned model to be more accurate on the best trajectory? We proposed conditioning the model on the goal and learning in a way such that it only captures the necessary information for that goal. We assume a self-supervised setting where we do not have access to any task-specific rewards at train time, and at test time, the aim is to plan using the learned model to reach unseen goals. To this end, we propose goal-aware prediction, or GAP. Unlike a normal lane dynamics model, which encodes the current observation, GAP encodes both the current observation and goal into a lane space. Gap then reconstructs the difference between the current state and goal from the lane encoding instead of the full observation. As a result, the lane space does not need to capture any information about the task irrelevant object, such as the green block in this case. Then forward dynamics are learned in this lane space. Critically, since we're in the self-supervised setting, we don't have access to true goals. Instead, we leverage hindsight relabeling to acquire goal-reaching trajectories. In our experiments, we examined 3 primary questions. First, how does gap redistribute model prediction error? Second, how does using gap lead to better downstream performance on control tasks? And lastly, does gap scale for real cluttered visual scenes? In our experiments, we tested on a suite of simulated robot manipulation tasks, as well as real robot manipulation data sets. First, we examine how gap redistributes model error in the simulated domain. We do so by sampling 1,000 random trajectories for an unseen task and ranking them by their true task cost. We then measure the model prediction error over the prediction horizon, average across the top k trajectories, where smaller values of k indicate better trajectories. We compare gap in blue to the standard lane dynamics model in orange, and observed that while over all 1,000 trajectories, the performance is roughly the same, while looking at better and better subsets of trajectories, gap has relatively lower prediction error. This suggests that gap is more accurate on the best trajectories. We observe this qualitatively as well, where gap more effectively models the target object in a good trajectory, seen in the middle, and does not model task irrelevant objects at all, as seen in the predictions on the bad trajectory in the bottom. Next, we examine if gap improves downstream task performance on unseen tasks in a simulated manipulation domain, testing on the block or door manipulation task shown in the top right. We report the task success rate when used with sampling-based planning. We find that compared to the standard lane dynamics model, as well as the self-supervised model VRL technique rig, and a lane dynamics model learned with the inverse model objective, gap is the strongest performing method. Lastly, we study if gap can be applied to challenging real-world data sets and complex visual scenes. To do so, we combine gap with an action condition SVG video prediction model, where now, when combined with gap, the SVG is conditioned on the goal and predicts the sequence of goal state residuals. We compared these approaches in their test prediction error on goal-reaching trajectories on both the RoboNet and Bear Robot dataset, and find that gap and gap without residual prediction outperforms standard SVG. By conditioning on the reach goal, gap is able to focus its capacity on modeling the components of the scene which are relevant to the goal, as seen in the video on the bottom right. The key takeaways are, for model-based planning, model error on the best trajectories is most critical for task performance. Gap helps redistribute model error to be more accurate on task-relevant states, and using gap leads to improved downstream task performance. Thank you.
Okay, that's all the spotlights for this session. Do we have questions from audience? Okay, yeah, I have one question for Martina. In the paper you show a very simple cases for the real practice. So how about to extend to more complex scenario? Do you have a plan to extend the method to more complex scenario?
Do you mean for the box stacking task? Because currently we are both validating the approach on a box stacking task and on a folding task with a real t-shirt. So we are currently focusing on deformable objects and on using this method for deformable objects. So we think this is currently quite hard to achieve.
Okay, thank you. And another question is for team, and this is a very interesting topic, and you present a very interesting method to do these things. And I have a question about the scalar response. So how does the scalar response affect the final results? How does the mapping function affect the final results? Because I think this is also another things you need to tune, or how to make it. Tim, your speaker has something wrong. Yeah, now it's better. Oh.
Is it working now?
Yeah.
Can you just repeat the question? It was cutting out from my side.
Oh, yeah. My question is about the scalar sensory response. How does it affect the final results, or how does the mapping function affect the final results of your algorithm? Yeah.
So usually we learn in scheduled auxiliary control, we would learn different policies for the auxiliaries and for the final goal task. So the hope is that the auxiliaries do not bias the policy for the final goal task. But in the sense of whether we can learn the final goal task at all, it makes a huge difference because especially tasks like stacking or also the ball and cup, they are usually out of reach to learn without a proper exploration strategy.
Okay, I see.
I can ask a question for Suraj. So Suraj, you in the gap, you learn a goal condition model, right? Have you thought about problem with multiple goals? Like for example, in grasping, there could be multiple ways to grasp the objects. In that case, how does gap help?
Right. So in our setting, we get the goals basically via hindsight relabeling from the agent's own experience. So in all the settings we're looking at, we basically have a large offline data set, and then we relabel goals from that. And then the assumption is that at test time, you basically get a single goal state that you're trying to plan to reach. So right now, basically gap, we designed it to basically be conditioned on a single goal. It is possible that you could consider conditioning your dynamics model on multiple goals if there are multiple goals that basically can represent the task, like you said for grasping. Most of the main benefit where we see gap being helpful is in this like tabletop manipulation setting where there's many objects and you don't want to have to model the dynamics of all of them, just the relevant objects, and that's what kind of the goal conditioning gives you. So in the grasping case, if there's kind of only one object and you know that one object is the one which you need to model, there probably isn't a lot of information that you can kind of ignore by conditioning on the goal. So I would expect it to be less helpful in that case.
Yep.
Yeah, the last question is for Georgia. And in the paper, you present the bin mechanism for the grasp net. So how does the bin affect the final results? And yeah, maybe I missed that part in your paper, in your presentation. Yeah.
Yes, can you hear me?
Yeah.
So for the final results, yes, basically in the paper that I've submitted here in RSS, we just included the results regarding the visual representation. So just on the aspect of the visual reconstruction of the maps. For sure, the final result is not what you expect. So either in simulation or in the real world, the part that will finally select the actual best grasp from what appears to be the best grasp is very different. So what we are actually working now on is on a planning strategy using like this representation as a latent space for extracting some useful samples to create in the end the grasping policy, because the best visual grasp is not in the end the one that is also meaningful for executing the task. So I may also grasp an object and lift it up in the air, so this will give me a success, but in the end this grasp is not meaningful. But on the other hand, while disentangling these multiple orientations in the objects, it gives us some early results of how you can give different policies for manipulating the objects. So there is no one hard solution there, but different possible ones.
Okay, thank you. Thank you. Thank you to all the presenters, and yeah, thank you for your contribution to this workshop. Okay, let's move on to the next part. Yeah, Kwan, it's your turn.